Okay, I think we're ready. It's 8 o'clock. Yes. All right, so today we're mainly going to be in SolidWorks, but we'll have to do some other things because the simulation we're going to run in SolidWorks might take a little while to run, and we don't want to just sit there and stare at the screen and while it does its thing. So our main idea, though, is topology optimization. So topology optimization is a simulation process where, in this case, SolidWorks, but some kind of CAD package. SolidWorks for us is going to take some starter geometry. So we're going to build out something, I don't know, just some bracket or something. And it takes that, you load it like you're going to do a simulation, maybe a static analysis simulation. And then what it'll do is anywhere that there is unnecessary material, so depending on the loads and constraints that you put on it and the starter geometry that you define, it will remove material because it's unnecessary. So here is kind of a overview. Let's see, this one, yeah, that would work. So this is engineeringproductdesign.com, and you kind of have this progression of brackets here. I think this is actually I don't know how many years ago, several years ago, GE, General Electric, put out a challenge to redesign this bracket to whoever could redesign it, have the same function but less weight. And this is, I don't know if this is the winning bracket or just one of the brackets that was generated here, but you can kind of see the process. It goes from something that's very ordinary looking, so it's got some holes and very flat faces like it was machined, into something that is very different from that. It's spider webby, organic, still has the holes, so all the necessary holes are in the same places that they were before, but there's way less material in it. And so this is kind of the process, and what they're showing here is some intermediate ones, so maybe a little bit less weight reduction each step. So let's see if there's some other interesting. This is an article. Here's kind of the very broad overview that I was telling you about. So they've got the original part, so that's your design space. You have to give it, for topology optimization, you give it a starting part, and it's going to optimize that part. There's another process that we'll look at, I don't know if we'll look at this week or next time even, but soon, where it's generative design, where it kind of works backwards. You just give it the constraints. You have to have a hole here, don't put anything there, here are the loads, and it will generate material between those constraints. So that's a generative design, which is, they end up looking very similar, but topology optimization is technically the one we're going to look at today. And so we start out with some shape, and then the software will iterate, do a finite element analysis where it does the stress loads, well, the stresses based on the loads of your part, and anywhere it finds really low stress, it probably doesn't need material there, it will remove that material and do another cycle. So you usually give it some kind of goal, like I want to reduce mass by 40% or whatever. Usually it's a weight reduction is your goal. And so you tell it what its goal is, and it tries to achieve that goal by iterating through successive finite element analysis on the parts that it's generated. And then you end up with some final result. Now usually in this one, this probably was, they took the final results, smoothed them a little bit, and that was the final result. A lot of times you don't do that approach. What you do is you take the final results and use those to manually remove material from your original design so they don't look quite as organic. But a lot of times the final results are, they're a little bit too unusual, I guess, and so you don't just smooth the mesh and print that out, although you can do that. That's what these are kind of leading towards, is you just smooth this mesh out and print it out. Now you do have to do one other step that I didn't mention there, is you get your final optimized geometry, then you need to run the simulation on that geometry to make sure it's still valid. One thing that you can run into, and this is true with any finite element analysis, is that it is optimized for whatever exact loading situation you put in there. If the loading situation changes somehow, you get a load that you didn't simulate for, then that optimized geometry may not work anymore because you are putting it under a load that it wasn't optimized for. So you have to be careful with that, but that's true with just finite element analysis in general. Here's kind of an overview of the whole process. Import some geometry. We're just going to build our own. Define any preserves. So there are some places you have to keep material, or you have to keep material out of a hole, or you have to keep some border around a flange or something that it has to stay there, and it doesn't have a lot of load around it, so it might get chewed away in the process, but you want to keep that, so you define any kind of geometry you have to keep. Then you put your loads and constraints just like you would on any other simulation. You generate the mesh. This actually says generate and adjust the mesh. We're not going to adjust the mesh. We're just going to take whatever mesh it gives us. But realistically, when you're doing a finite element analysis of any kind, whether it's just a static or a topology optimization or some kind of other simulation, you probably should go in and actually optimize the mesh itself, all the little elements. But we're going to skip that step just for, it's going to be good enough for what we're doing. It will, you give it some sort of objective. So I don't know if you can read that, but it says mass is less than 50% and of the original part, and you maximize the stiffness. So it's only going to remove material that is having the least amount of effect on the stiffness of the part. Then you run the study. These studies can take a while, so that's why I'm thinking that while the study's running, we'll do something on the printer. Then you evaluate the results. You take that exported result and either you edit the original geometry based on the exported results of here's what material you really need. That's probably what we'll do. Or you smooth the mesh that's generated and you just use that directly. And then you go back and whatever you decide to do, you run the simulation again and make sure that you didn't inadvertently create some part that's not going to work under your loads. So that's kind of the overall process. I don't know if there's any other. Oh, just here's an extreme example. I don't even know if this is real or if this is a render. I'm not sure. But here you've got a motorcycle chassis that's all been optimized here. So you can kind of see that's kind of the thing that you're going to do. And usually the whole goal is weight reduction. So it shows up in aerospace, racing, stuff like that, where you're trying to make sure that you've got the lightest weight, whatever it is, in this case, chassis and swing arm, but whatever you might need to optimize for weight reduction. 3D printing comes in particularly when you're dealing with this kind of geometry here, where you could probably make that with a robotic CNC arm and enough fixturing. You could get in there and make all these shapes, but it's really not ideal. You can still use, if that's what you have, maybe you have a water jet or a laser or a regular CNC mill. You can still use topology optimization on flat pieces. Even castings you can use topology optimization, but it really shows up in additive fabrication, where you have really any geometry you want to make, you can make. These are metals. Maybe it doesn't make quite as much sense for 3D printed FDM plastics because you can achieve weight reduction just by making the infill lighter. And so maybe it doesn't quite make as much sense. It looks cooler, but you may get the same results by just modifying the infill of your printed part. But maybe you don't want that. Maybe you want a solid part, but you want it to be lightweight, and so you have to come up with this kind of geometry here. The FDM printed stuff, you still have the issue of layer adhesion, which is not simulated in this process. So as far as I know, there aren't any finite element analysis specifically for FDM printing that simulates layer adhesion issues. You know, it all assumes that the material is equally strong in every direction, which for FDM that's not true. You know, it's between the layers it is significantly weaker than across the layers. All right, so let's go start up some of this. I've already started SolidWorks somewhere. Now this might be, oh, I guess I closed SolidWorks. Thought I had SolidWorks running. Let's restart SolidWorks so that we can do this. And I'm using 2021-22 version. This process should work for most of the recent ones. There is one step in here that I'll probably use towards the end, that 2018 or higher is when they started using that step, but it's kind of minor, so it doesn't matter too much. This does require the simulation premium package to do the topology optimization. So in your SolidWorks add-ins, in your simulation, if you have, oh, I don't remember which one it is. It might be simulation premium. It's the higher end one. I don't remember which one it is. But without that, you won't have access to topology optimization. You can still do static load simulation, but not the topology optimization, I think. So I think it's this one. We'll see. If it's not, we'll load the other one. I'll go ahead and load that one if I haven't already loaded. It looks like it's not in there yet. So it does have to have that. So the base level SolidWorks won't do this. It does have to have one of the higher end ones. Normally this is a pretty heavy duty process. Also for SolidWorks, they run this locally on your machine. So it's going to be highly dependent on what your machine specs are on how long this takes to run. So with mine trying to stream, I don't know. It might not do very soon. We might have to come back to it later. I thought what we would do is, we still have this guy. We still have to make this. This is not what we're going to do today. We still have to make that, and we still have to make some front landing gear. There's a big hole there. But I thought we would make a stand for this, because that would be relatively straightforward. There are a couple of holes here we could use. The center of gravity is right around in here for the thing, so I'm not going to worry too much about actually making an interface with the jet, the X30 right now, but for our pretend use case, that will be what we're assuming we're making, is some kind of base that will hold this jet up somehow. Doesn't really matter how. So our little cover came off. We need to tighten up this little nub right here. Isn't quite large enough, but everything else on it fits pretty well, other than the color. The color's way off on that one, but that's just a function of the filament that I had. Let's see, the SolidWorks yes, SolidWorks is back. All right, so let's go over here and let's get all our buttons on the screen so you can see them. I don't think we need anything up there anyway. First, let's create our base geometry. So let's just do something pretty straightforward, just to show the idea here, because I do want something that hopefully will simulate soon enough that we can actually use it today. Let's go on the front plane, and let's just worry about the arm. Let's not worry about the actual base itself that the arm will connect to. The base will sit on the table or something like that. And let's not worry too much about how it's going to interface with the jet. Let's just assume we can add that later. And let's just do the arm. So I'm thinking of the arm as some sort of almost a C shape that's wider at the bottom, narrow at the top, and it'll be able to, somehow go into our hole here to kind of hold it up, and it'll come somewhere down in here, somewhere like that. So we're not going to be too worried. I'm in a sketch view over here, and let's put a where's the origin? Let's put a line down here. Oh, so my computer has redraw issues when it's streaming, so it will clear up. But oh, you know what? I'm using keystrokes that work for Fusion, not SolidWorks. All I did is turn that into a construction line. Get off of there. Let's see. I don't want to filter. There we go. All right, so that's just my baseline where the ground is. I am in, let's see what units. I'm off the screen for my units. All right, I'm in inches right now. That's fine for this. So looking at this, I think it should probably be, I don't know, I've got a ruler over here. Let's see. Six inches total height or so. So I'm just kind of going in and defining some areas for me to work in. It's gonna be annoying with the redraw issues, but whenever I stream, it just does that. I don't know. I've tried to fix it before, and I'm sure there's some way, but usually zooming in and out redraws it to where it's not all that crazy lines. So those are my two little construction lines that are 6 inches apart, and I'm just going to put some kind of, I'll do a spline, I guess. So we'll grab that line, and it's kind of hard to imagine what line I'm actually drawing here. That one? Okay. That's kind of what I was thinking, but maybe more like that. Something like that. I don't want to just offset it though, so let's make the base something like that. That looks reasonable. This is going to be a really sharp angle up here, but we'll fix that in a second. In fact, why don't we fix it now, I guess. Let's put some little way that this is going to interface with the plane. And we can make these corners a little bit smoother because those are a little crazy, aren't they? So there's a fillet for there and there. That's fine. It's just telling me that it's going to delete the right angle. That's fine. Really doesn't like doing all these things at once. Same thing there. It's going to delete the right angle. The top we'll leave squared off, but let's do dimension that. It looks like that. If that's going to interface with our plane, that needs to be maybe a 1/2 inch, and that cavity is actually pretty deep in there. So let's make this 0.5 inches. All right, now we got some weird stuff happening that we'll need to adjust. You know, now our shape here got because of the constraints we have there with the fillet. But we can do that, and probably something like that. Maybe it could be thinner. I don't know, something like that. Let's connect these bottom pieces together. Got a solid shape that looks good. Let's make this height a little bit more because that was, let's make that 2 inches. It really does go into the plane quite a ways. And I want to show a particular part of the process. All right, so that radius looks like it could be quite a bit larger. Oh, now we need to adjust this. I don't really want it to be too... I want to have some area for the process to actually do something. Let's say that that's what we end up with. We could spend a lot of time doing that, and maybe I will later. Let's make it thick enough that it's not going to be too wobbly. So let's actually make it a 1/2 inch thick, maybe. Is that good? I think that's probably good. The plane's relatively heavy. Let's make it 3/4 of an inch thick. We're gonna eat away most of the material anyway, so. Oops, not 7.5. 0.75. There we go. All right. So let's say that we're happy with this as our shape. Now what we do, let's save it, because who knows if it's going to crash on us. I don't want to put it in the down. Let's put it on the desktop. This will be the X. I don't know if I can use minus signs in X30 stand. Not the whole stand, but there would still be a base, and probably something up here would be different on how it's actually going to fit into the plane and interface with it. They do make some of these that are just acrylic, and they hold the plane up, but we're just going to do this. All right, we could fillet these corners. I kind of think we should do that because the process will potentially fillet these things, but maybe it won't. Oh, I know what we could do. And actually it affects the thickness. Let's actually make this thickness, no, this one. Let's make it a nice even number, 0.8 inches. And I want to do that because I think where I made it, let's see, the front plane is actually, yeah, it's on the back side of it. I want a mid plane. So let's do a reference geometry plane. And it'll be parallel to the front plane, offset by 0.4, so that it's right in the middle of the thing. You can kind of see it there. I guess I could have clicked MIG plane and done the two surfaces. What I want to do with this plane is, part of this process could be that I want it to be symmetric, or left and right, or up and down, or whatever. I want to be nice and even on both sides. Otherwise, it may not do that. It might create uneven geometry. You know, the front side is different from the back side, but I want them to stay the same. Plus, technically, it'll make it run a little bit faster because it's only having to simulate half the model. So I put a plane right through the center of it, and I'll use that as a mid plane later on. Let's see. Let's go to our simulation now. I was wondering about filleting. Let's just see what a fillet looks like on this edge. If it, I kind of like that, but let's also add that edge, and let's see if it'll do that edge and that edge, just where it's not a perfect rectangle, or, well, I guess it's not a rectangle. The top part is. Could we make it a little larger? What is 0.2? Yeah, that's kind of nice. Let's do that. All right. Got some weirdness right in there, but that's okay for what we're doing. All right. Now let's go to our simulation. And we're going to do a new study. And this is where, if you did just I think the SolidWorks simulation, not the SolidWorks simulation premium, then you would only have this one button. All these other buttons would be here, but they'd be grayed out. And you could only do a static simulation, which would just be the one loading configuration, and it's a static load. And it'll do the finite element analysis for that one thing, but we want it to, not recursively, but continually, iteratively, that's the word, do the topology study, and so we need that part. So topology study is right here. We'll leave all of that alone. We do need to give it a material. So because it's going to do an actual simulation, it needs to know what material this is. I don't know if I have a nice plastic. Oh, I think we need to open up. I don't know if I've got a plastic material loaded into here at all, but again, even if I have one that is of ABS or PLA or whatever, it's not going to be FDM printed. It's not going to have those properties. Let's see, we've got plastics right here. There is an ABS. Is that going to be our best bet? I think so. Let's just use that. All right. Now we have a material applied to it, so there's a little check mark in our topology study. Connections, we don't need any connections here. It is going to connect to the plane, but that's not really what we're going to do. Fixtures, we do need some fixtures. I'm just going to make this bottom right here totally fixed. That's where it's attached to the base. The base isn't part of this thing. We would have some kind of, I don't know, oval base that this would be part of. Maybe it would glue to it, or maybe I would probably have it glued but inserted into a matching slot in the base. So we'll just make that completely fixed. External load, so the plane is going to sit up here. Now I'm going to be relatively simple with the loads and just say it's a force on this surface up here, but it probably has a multi-dimensional force from a couple of different angles, but we're just going to do this. Let's use English system, and I haven't weighed this. Let's see, I have a scale right here. Let's see. Oh, lost a missile. All right, so it's almost a pound, and it's missing a couple of parts. So let's say it's a pound, but I want this to not be right at the limit. So let's say that, I don't know, 3 pounds maybe? We'll do 3 pounds. Okay, so now we've got, I'm trying to get it in the view here. There we go. We've got our load, our material, and our configuration, or not our configuration, our constraint. Now we need, this is goals, and I've been using the word constraint for that fixed geometry. Constraints in this particular thing, what they mean is, well, let's click on it, and I can set up some goals that I want my design, my topology optimization to try and achieve. I think minimize mass is probably the one that I'm going to do for the results I want. Best stiffness to weight ratio might also be a good one, because that includes a minimized weight while you're still trying to keep it stiff. So let's use that one. So I want to reduce mass by 30%. It currently says that it weighs, well, we're in kilograms. So current mass of 0.17 kilograms. What is that in pounds? Let's see. Um, 2 pound? No, that's not that. Oh, this is not doing what I want. Third of a pound, somewhere around third of a pound. So it's not very heavy already, and I do want it to be heavy enough that it's not going to just slide around on me. Let's say that we want to reduce mass by 40%. So that actually will make it lighter, but I do want to have something happen in here. So I want it to be kind of aggressive, mainly so that it looks like we did something in the simulation. In the real life world, I may not actually go that aggressive. I can also say that I want to maintain a certain factor of safety against maybe von Mises, or let's see, I've got, well, or just a factor of safety. Factor of safety is greater than 2. That seems fine. I've already kind of got a factor of safety in there because I put a 3-pound load on it when it was only 1 pound. So, I don't know. We'll see. Uh-oh. This plastic doesn't have a yield strength. Alright, so let's not worry with factor of safety. Click off of there. I didn't pay any attention to the material properties in here. That might give us some trouble later on. Manufacturing controls. So let's add some preserved regions here. So I basically want to keep this part, and I want to keep it this shape for a certain distance because I want it to be able to go into the base, and I don't want it immediately to start eating away at this part right here. In fact, I could have made a little extrusion here, kind of like I did on the top, and that would have probably been better, but I'm not worried with it right now. But let's just say I want to preserve that for a 1/4 of an, oh wait, that's millimeters, 1/4 of an inch. Not meter. That would have preserved the whole thing. So let's get the right units in there. All right, so now you can kind of, well, it didn't actually show any. There it is. So it's going to preserve that much of it and not going to eat away at any of that part. And maybe I could go a little more down to 5.5 inches. There we go. Let's do that. Okay. I also need to preserve some of this top part up here. So add a preserved region, and we'll just go from the top down from there. That one I made 2 inches. Let's preserve that at least an inch. Let's switch over to inches. Oh, I didn't need to change the color. Okay. And then I've also got in here, well, thickness control, maybe part of what you're doing, the process itself, you can't have something that's thinner than a certain size. Maybe you're doing a casting, and if it gets too thin, it can't really cast very well. Or maybe even some of the metal additive manufacturing processes, if you try to print too thin, even though the geometry says to print it, it won't print very well. So there might be a minimum thickness that you have to maintain. I don't really have that here. I guess there is some, but this is really more for flat pieces. Demold direction. So if you, this can be, it says demold, so that's more like casting or injection molding or something, but it could be also a milling process where you can only mill from one direction. And so you could use this demold to specify that, hey, I only want to mill from one direction. That means that all the material has to be cut away from that side only. We don't really have that with 3D printing, but I do have this symmetry planes. That's why I made this plane 1 here. And we can do half symmetry, 1/4 symmetry, or 1/8 symmetry, like it's a radial thing. We'll do half symmetry and select plane 1. That way it only has to solve half the model and just mirror the other half. Okay. There's all of our little constraints. So the color tells us that there's a material on there. It's kind of still gray. We've got a load here, a load here. There's our symmetry plane. And it doesn't really, it's not showing up, but we had these preserved regions on the top and bottom. Okay. Now is the part that I don't really know how long it's going to take. So up at the top, I'm just going to run this. I haven't actually meshed it yet. So technically, if you're doing this for real, you need to go in and mesh and then check the mesh to make sure that it is a good mesh and there's no really strange elements in there. You have elements the right size in the right places and all that kind of stuff. It's generally pretty good at generating usable meshes. But I'm not going to get into, this isn't a class for finite element analysis, so we're just going to run the study. So it's going to mesh, and then it will start the study, which I really don't know how long it's going to take, but we'll let it pop up the first window, and then we'll probably go do something else. All right, so we can allow it to check our license. So iteration 1, and there's no specific number of iterations. So it's going to run the first study. So it's basically going to do a static analysis of exactly what we have right now. And then it's going to, based on those results, anywhere that there's low stress, and it can remove material without really affecting the stiffness, because I did best stiffness to weight ratio as a control. It will remove material from there and rerun the study with the same constraints and everything, and it'll keep doing that until it has either failed, it can't converge to a solution, I've asked it to reduce too much mass or whatever, or it's gotten to that 40% mass reduction and it has found a valid solution. So it's actually going decently fast. It's already on iteration number 5 right now. We did not ask for super complicated geometry, so it shouldn't take terribly long to do it. And this computer's decently powerful, I guess. It's not super powerful, and it's kind of old, but it does have a lot of memory on it, so maybe that's helping out here. But well, you can get an idea of how long it's going to take with these convergence data graphs. So there's my best stiffness goal. If I show the graph here, you can kind of see, I don't know if you can see well, I'll make it larger. But see how it looks like it might be turning the corner here to where it's going to level off, and that would be good if it gets to a stable solution. Let's see the other one. The mass. So is it close to the target? So here, there's the target apparently. No, that's the original, isn't it? No, that's the target. That's the target line. And it started approaching it, and then it made a choice that sent it away from the target, so that wasn't so good. But hopefully it can correct and get up to our target. It may not be able to. Maybe 3 pounds with that material and those dimensions can't be reduced by 40% and still maintain the... well, I removed the factor of safety constraint because it didn't have a yield strength. Look, it's going the wrong direction. So it is starting to turn back around, so maybe it'll turn around, but that's kind of making me think it's, oh wow. Oh wait, no. No, it is 0.1. I'm not sure what it's doing here. It actually had gotten down to something that was even less. Huh. I don't know. 0.101. I don't know why it's got the line. Maybe that's the original weight. It says that's the target value. So it actually had found some that were even less mass. Unless this is the mass removed. Maybe that's the amount of mass removed. I can't tell. It looks like it's the target mass though. Yeah, that was the target mass for it, 0.1 kilograms. Now it's headed in the right direction. Let's check our other graph and see where it's headed. Oh yeah, it's starting to stable off. So, I don't know. It looks like maybe in the 20 to 30 iterations, we might get there. I lost my window. Let's see, there it is. Now it says it's 24% done, but I don't know that that's true. We're on actually iteration 19 already. So, while it's doing its thing, I'll tell you a little bit of what we've got coming up over here. Oh, well, you've seen these. These are our HueForge print that you can do this with any printer. It's just a lot of manual filament changes, and you have to have different colors of filament. But that's HueForge. We did the also with any printer you can do the lithophanes. They're usually one color, although you can make them color. This one's not going to show up very well on a camera, but in real life they look pretty nice. So we've already looked at those. I'm going to try. I've ordered some. Well, oh, speaking of order, was it last time? think it was last time, we ordered one of these plates, and it came in, these build plates. I haven't printed any, I haven't even taken it out of the package yet. But to see how this one works, we've ordered one of these. That actually shows up pretty well on camera. So we ordered this one. It's got a film on it we have to remove first, but I don't want to do that just yet. So when we print on this pattern should be built into whatever is touching the build plate. And then the other side had a different pattern on it. So a little bit different pattern. So we bought that off of Amazon. I'll show you which one it was once I find it. We're on iteration, still going. I don't know what number it was. This one. So we got this guy. So it was 16. Actually, I don't remember if we got it at that price or not, but now it's $16. There was another one that was a little bit different looking, but this one, you don't have to. It is a magnetic bed, so you can, if you have a magnetic sheet on your printer, you can just switch them out. But even if you don't have that, you can use the little binder clamps. It doesn't come with any, but you can use little binder clips, like for paper, to hold it on the bed that you do have, even if it's not magnetic. So ours does happen to be magnetic, so all we have to do is, there's the steel one that we had on there. Take that one off and peel the film off. I'll do that later, and snap it on there. Now this one does have the bed sensor, so there is that's a CR touch. There's a BO touch, CR touch. There's a lot of different bed sensors. Since this one has a bed sensor, I don't have to worry about this being thicker or thinner than whatever was on there before, or being on top of something that was already on there. The bed sensor will go and probe the bed and adjust for it. If you don't have a probe of some sort, then you will have to change your Z offset potentially if you, well, certainly if you put this on top of another bed. But even if going from this sheet to that sheet, this one's slightly thicker. It's like 0.5 millimeter thicker or so. So you have to adjust for your Z offset if you don't have any kind of bed probe. So we'll print on that and see how it's going, how it works. Oh, we've got some results. They're not very exciting, but we do have results. All right. So, and this is what you end up with. So it says that I really can't remove much here. I made it too thin, but you can do a little bit down in here. So I can basically chop off that corner. It only kept this part down here probably because I told it to preserve the region. Same thing up here. It did say that, hey, you could probably get rid of a little bit here, although that doesn't seem worth it to me. That doesn't really do anything. So we got a little bit of interesting stuff here. So this big chunk can go. That big chunk is unnecessary. There might be a little bit of room we could punch out there. It's not as interesting as the one that we looked at online with the, this kind of thing. Didn't come out that quite interesting. Maybe if we had asked for more mass reduction, we could have been able to achieve that, because I don't know. It does say must keep all the yellow, so most of it's yellow. All right. So let's say that you're good with whatever you got here. So that's not super interesting. I was hoping for something more like the, more like that, but we didn't get that. So now what do you do? So you got a couple of options. One is, since we are going to 3D print it, we can just print this. So I actually want to save first. I don't want it crashing. Let's just make sure it saves. Doesn't have an auto save. Also, I use this plane one, so I have a mirror image. If I don't do the split plane, I don't remember exactly what it called it now, symmetry control, then it could be that this side looks a little bit different from this side, and for this particular part I don't want that. I want it to be symmetric. So I can right click on this guy and I can export the smooth mesh. So I can just let's make it a new configuration. So I don't know if you've used configurations much in SolidWorks, but It's a pretty handy tool. It's this little tab right here in the middle. I don't know if you can, right over here. The configuration idea is that you've got one part and maybe there are several different applications for that part. In this case, I've got the solid part and then I've got the mesh reduced part. So that's two different configurations of the same thing, and you can use configurations to speed up modeling when you have one part that has several different applications with slightly different hole patterns, or maybe they've got different finishes on them, whatever is different about them. Most of it's the same, but they have some little tweaks to each configuration. That's the configurations are an easy way to deal with that. So I will make it a new configuration. It's just going to name it Topology Study 1 Smooth Mesh. That's fine. And it's doing its thing. It is smoothing the mesh. So now, a little bit smoother than it was before. You could, oh, well, there is a little bit interesting I didn't notice. So it's actually hollow in there. So I wish it had eaten away from the outside in, but it looks like it ate away from the inside out, and it didn't get all the way to the surface here except for that little hole there. But it is a little more interesting than at first I thought, because there's a pocket in there. So that would make this particular thing actually kind of hard to machine, right? Or to mold in any way, because you'd have to have some removable core if you're molding this or casting this. And to machine it, you'd have to have a 6-axis robotic arm with a long mill bit to get up in there to do that. So, but 3D printing, we can probably do that relatively easily. Now this does not, it looks kind of like a giraffe, doesn't it? Doesn't look like it's super exciting, but let's just say that we're happy with it. We could now, that it's a mesh, it's an STL file, or well, we can click on it and, do I have to? I'm thinking of, sorry, I'm thinking of Fusion. I think we go to File, Save As. And we can tell it to save it as a STL file. So we can just save it as a STL, throw it in our printer, and print it. We'd have to figure out the supports, because it might need some supports in there. It did not create this geometry specifically with the idea that it's going to be 3D printed and I don't want supports or anything. So it didn't think about anything overhangs, or it didn't think of any of that stuff. Although I think it would probably print okay with no supports. These right here might be a little bit shallow of an angle to print with no supports. Not sure. This one in particular. All right. So that's one thing you could do. The other thing we could do is, let's look at our configuration. So if I go over to configurations over here, if I can get some more room in my window, I'll show them to you. So now I've got two little things. Currently I'm looking at the smooth mesh. If I want to go back to the other thing, I can just double click and there's my original part I made. So in the view, is mine not going to have that in here, or is it only in this one? So maybe they have changed. What I wanted to do was I wanted to overlay the meshed body into the part, the original part, but it's not showing it here. I might have to investigate why this. I have different versions at work and here, and maybe it should be in 2018 and up though. And this is 2021 or 2. Well, is it in display style? No, no. I wonder if they moved it, or maybe I'm just stuck in another. Oh, I'm stuck in the topology. Let's go back to the model. Maybe if I'm in the model. Nope, I only have cartoon and perspective. Huh. Oh, there it is. All right, so here's the process. You got to be in the right. So I've got to be in the model down here at the bottom. You know, I've got all the tabs. There's my topology study that I did. There's the actual model I built down here. And then in my configurations, I need to be in the original configuration, the default thing that I made. And then when I go to the view settings, I can do simulation display. And what this will do is, even if it's not a topology study, maybe you just did a simulation of whatever, I think it'll work with others. But if I click simulation display as my view, then it'll tell me what it's going to do, and I can click OK. And I might have more than one study, so I've only got one, so I'll pick the one that I do have. And what it'll do is, well, it still isn't quite doing the right thing though. There we go. If I select the boss, it'll show the original shape overlaid with the simulation study. So it puts them exactly on top of one another. And this is probably more like what you would do if you were going to analyze this thing and create a light-weighted part based on your original geometry. So you've got my original geometry, and I've got the simulation overlaid on top of it. And now I can go in and I can create a extruded cut. We'll just go with this front plane here, and we can use this to go in and draw. Oh yeah, so I do have the weirdness going on here with this. I can draw geometry that I'm going to use to cut out the shape. Now I probably want those to line up, so something like that, that, and then we'll get this one too. Now I'm going to have all kinds of weird constraints and you know, things like that may or may not be what I want. Let's do round these off though. Let's do fillets on all of these. Oh, that one didn't do a fillet. I have to do different fillets on those. That one I'm just going to cut out. Let's only fillet that side. And then these I have to make smaller fillets on. That's a bit much. Let's do 05. It makes a circle. Let's make it 03. All right. So I've drawn in. Now what I haven't done here is, this doesn't make this pocket inside here, so that's a little annoying. But we're not doing this too professionally right now. So now we can finish our sketch, and we can cut both directions. And then we can go back to our, I probably should have made a new configuration for this, but I'm actually cutting out the original part here. So technically what I should have done is made a copy of this configuration so that I could edit it instead of working on the original one. But that's okay, I didn't do that. So now what I've got is I've got a more controlled version of the shape that I was creating the mesh from. I still have the mesh, you know, if I want the mesh, the smooth mesh, still have that, and it does have that pocket in there, you know, all in there. But I also have a more engineered version of it, but without the pocket in there. I could go in and try to, you know, scoop out some of that. Once you're satisfied that this is what you need, you still need to go back and run your simulation study on this guy though, because if you don't run, you know, because you made this one not maybe you overlooked something. This one should actually be stronger because it doesn't have this mass removed. But whatever you end up with, you should take that geometry, even if it's just this. Even if it's just this guy, you should take this and run the simulation on the actual final geometry to make sure that it's still going to work the way you intended it to. So that's kind of a overview for this. Is called topology optimization. Ours didn't come up with quite as interesting of a optimized part. Maybe I'll make a new one that's going to be a little more interesting than this. But I think we could actually come up with a interesting part with just some printing techniques that's cooler than this one. And maybe we'll try that too. All right, we've got a little bit of time left. I think we've done all that we can do today. I will print something on here. Oh, the other thing I'm going to show you is upcoming. This one I'm not sure how well it's going to work. I've seen it done a little bit, but I've got some of this. So this is the inkjet version, and I ordered some toner version, so like a laser printer. These are transfer sheets where you, some of them you iron on. There are different processes, but I've seen it done where you print on here like you normally would. Normally you put this on like a t-shirt or a bag or something, but you print it, put it on your print bed, print your part onto there, and the transfer happens from here to your printed part. So you can actually have full color on your printed part. Now it's only on that bottom flat surface, but maybe there's some interesting things that you could do with a panel. You want to do a panel, a control panel with labels and that sort of thing on it, or maybe you just want a picture for some reason on a plastic piece. Maybe that's interesting. And it'll be full color, assuming that you have a full color laser. This one is inkjet though, so inkjets are full color. I haven't seen it work as well with the inkjet, so I'm going to try it, and then we'll also try it with the toner transfer paper and see if either of them work reasonably well. I don't know if we'll get to that tomorrow. Not tomorrow, Wednesday, because I don't know if the toner paper will be in or not. The other thing is we're going to do a nozzle change. We've already done a nozzle change once, but we're going to put a larger, like this is a 0.8 millimeter nozzle. So we're going to put that guy in there. I may do that on the stream. It doesn't take too long, and it might be good to refresh in case you missed the nozzle change before. But with 0.8 millimeter nozzle, now we can start printing some much thicker lines. Normally you don't want that, right? You want really thin lines that you don't see, but there might be cases where you want a big thick line because you want that texture on the surface, or maybe you just want it to print faster. And so we'll put a larger nozzle. They do make larger than 0.8. That's just the largest one I have. And then I do have some that are 0.2, I think is in here. I think there's a 0.2. Let's see if I can read it. No, that's a 0.4. What about this one? Also a 0.4. I thought I had some smaller ones. 0.25. Okay. So, let's see if we can see these. Where'd they go? So, 0.8, 0.25. We'll go and put the 0.25 in there and see if we can print some very fine details. So big and bulky prints with hopefully fat lines that print pretty fast. Very thin, probably takes a long time to print, might be hard to tune, and should be able to get high detail if we can get it tuned. I have always had trouble tuning the really thin, not the little small diameter nozzles, but we'll try and see what we can do. All right, so that gives you a new, if you have SolidWorks. So if you have the education version, the full-blown education version of SolidWorks, you have this option in there. You might have to go in and in your add-ins, make sure you use the Simulation Premium, not just SolidWorks Premium, and you'll have access to it. Otherwise, it's in the much higher end packages of SolidWorks that you probably don't have access to. It's not in base SolidWorks, so it is one of the premium things. But you can play around with that. The next time, maybe on Wednesday, what we'll do is we'll do the same thing in Fusion. Fusion does the other process, the generative design. So basically we'll say we need a base here and we need a connecting point up here. You build us something in between. We'll have to do some preserved and obstacle geometry for that one to make it any kind of curve shape or not. But we'll see what it produces. It does a little bit different process because it does not run locally. You actually upload it to the cloud. And same thing, if you have the education version, you should have some credits, or at least it doesn't cost you anything. But if you don't have that kind of thing, it does cost per simulation. So you don't have to buy the whole package. It costs per generative design process that you run. I think it runs on like the Amazon Web Services, and you have to pay for access to that. But we should be able to do that with some education license. So we'll see what maybe it'll come up with something a little more interesting than this guy. All right, so that's what's coming up. I don't know which one we'll do on Wednesday. Probably do the Fusion thing just to finish off this and see what it looks like. But we might have to do some of these others because it does take a longer time, because you have to send it away and it will get sent back to you on some schedule. But it doesn't run locally, so you can keep doing whatever you wanted to do on your computer without tying it up. So we'll be back Wednesday morning, and I'll see y'all then. Oh, there's a question. Okay, so this is a totally different thing. Is basic measurements taught every quarter? No, only fall and winter. Fall and winter is basic measurements, 382. So, and there should be 2 sections in the fall and 1 section in the winter, and hopefully one of those will work for you.